Hello everyone. So today we're going to continue on 6.5. Hopefully today's video should be the last video for 6.5. And then the next video will start on chapter 7, which is integral calculus, where we're going to start talking about integration. So very exciting. But let's finish up 6.5 first. So if I recall from last video, we get to talk about two different coordinate system already. The first is polar, which go from U2 to R2. Basically just mean it's a transformation that stay in two-dimensional space. And then we talk about spherical coordinate system, which actually work in from a R3 space to R3 space. So now we're going to talk about the last coordinate system that we will talk about, and that is also from R3 to R3. And so if you don't believe the Earth is spherical, but instead believe that the Earth is flat, then here is the coordinate system for you. It's called a cylindrical coordinate system. So basically, as the name suggests, is that we kind of talk about things as in they are cylinder, which is basically what a flat Earth will look like. It look like a circular disc, which is a cylinder, technically speaking. So here's the coordinate system. So here's the transformation. Let U3, let T be a function number from U3 to R3. And the transformation is R theta Z, T of R theta Z, which is equal to R cosine theta, R sine theta Z. And that's just equal to XYZ. And yes, if you look at this, you might be thinking like, wait, that doesn't, the Z just stays the same? Yes, it is. In the cylindrical coordinate system, you're basically taking the polar coordinate system and just simply add a Z coordinate that move it up and down, which is basically what a cylinder is. A cylinder is basically a circle that moving from one end to the other end, and that's from a cylinder. And here's the domain with domain U3, which basically is this. R go from 0 to infinity. That's the same as the polar coordinate system. Theta go from 0 to 2 pi. Same as polar coordinate system. Z can be just anything from negative infinity to positive infinity, which is the same as in the rectangular coordinate system. Okay, so show you how this one works. So I'm going to describe each of these variables. So pretty simple. R is actually slightly different. Is the radial distance from the z-axis to the position. So this one is actually very different because it's not from the origin to the position, but from the z-axis. So what does that mean? So let's show you. So here's our typical XY Z space. And let's say we want to define a position right here. So the distance R is actually defined to be more properly defined this way. Imagine that we take this point and form a projection onto the XY plane. Then I can define this distance right here from the origin to the projection as R. And that distance would technically speaking be the same distance as this point to, ooh, actually maybe I can draw it better. To the z-axis. So therefore, you can also call R to be the distance from the origin to the projection of the position on the XY plane, if you want to write it that way. And if that would make you understand what R is better, then you can go ahead and do that. But probably the easiest way to think of what R is basically the same exact R as in polar coordinate system. What is theta? Theta is basically the counterclockwise position, angle of rotation on the XY plane. So is the angle of rotation on the xy plane from the positive x-axis to the projection in the counterclockwise direction. And guess what? Theta actually defined the same way as theta in polar coordinates. As a matter of fact, if you simply use these two things alone, you can define the projection right here to be r cosine theta, r sine theta, 0. Which is basically just the polar coordinate of the projection on the xy plane. And then z is simply just being the distance, sine the distance, meaning that it can be positive, can be negative. From the xy plane. Which is basically what this distance is. And maybe right this way. And therefore make this point exactly the same thing as the projection r sine theta, r cosine theta, except that it now have a z coordinate. That is how far it is to rise up to where the position is. So as you can see, this cylindrical coordinate system is basically a polar coordinate system with the z coordinate added in. And that's why it's actually very easy to use, relatively speaking, almost identical to using polar coordinate system. And so if you believe the Earth is flat, then this will be a coordinate system for you. Let's talk about the inverse function. The inverse transformation is basically this, is T inverse of xyz, and the inverse transformation is actually exactly the same as the polar, because z just stays the same and you just basically transform x and y into r and theta. So that would be x squared plus y squared tangent inverse of y over x and z, and that's equal to xyz. And I guess I'm right a third time. So here once again is the tangent inverse that you have to make sure you pay attention to, with inverse tangent suitably defined to give theta in the correct quadrants. And that is the cylindrical coordinate system. So one last thing I want to talk to you about is the following. Whenever we have a coordinate transformation, one of the interesting thing about it is that because the transformation, if we have something in the, let's say, r theta coordinate system, like in the polar coordinate system, and let's say this point right here, what if this point start to move? Well, when this point start to move, it will change r and theta, and therefore changing x and y. So the question is there some way to actually account for the change? And of course there is, and when we try to account for the change, we are essentially trying to calculate derivatives. And this derivative actually, because it's a coordinate transformation that is multiple independent and dependent variable, its derivative is actually a matrix, a derivative matrix. And this derivative matrix actually has a special name. It's called a Jacobian derivative, Jacobian matrix. So what is a Jacobian matrix? A Jacobian matrix, and of course, a Jacobian matrix, of course, is named after the mathematician Jacobi. A Jacobian matrix is basically the derivative matrix of a coordinate transformation. One of the most important things about the Jacobian matrix is that because it's a coordinate transformation, when things change within one coordinate system, it will have an impact on the other coordinate system. Now, that is not surprising because, I mean, you know, it makes sense if I change the coordinate system r theta. If I change the coordinate r theta to something different, then obviously it would define at different points, therefore require different x and y to define it. That's like kind of common sense. What's interesting is that when we do that, we want to know how to change a correspondent. More importantly, which is what we're going to work toward later on, is that what if we take a region in one coordinate system and put it through a transformation, and based on the fact that the coordinate transformation is a transformation, it will change the shape of the regions. What we want to eventually figure out is what is the relationship between those two regions, because they will probably not going to be the same shape, and when they're not the same shape, they might change in area or volume, and that becomes something that's extremely important when we try to find area and volume. So that will be discussed later on in chapter 7.4. So we are just laying the foundation of that. So what we're going to do as last thing, so hopefully today's video will be relatively short, is what I want to do is to talk about the Jacobian matrix of these three coordinate systems that we have. So start with polar coordinate system. Polar coordinates. So we know polar coordinates is T of r theta is equal to r cosine theta, r sine theta. So then the Jacobian matrix for polar coordinates, the Jacobian matrix for polar coordinates will simply just be T prime of r theta. And notice that because T is a function that met from R2 to R2, our matrix is a 2 by 2 matrix. As a matter of fact, all Jacobian matrix are square matrix because it has to come from a coordinate transformation, which have to be a function that met from Rn to Rn. So if you simply just take the derivative, the first would be r cosine theta with r, that would be cosine theta. And the r cosine theta with theta will be negative r sine theta. And then this will be sine theta and r cosine theta. So that become our Jacobian matrix for the polar coordinate system. Spatial coordinate system is probably the most complicated one. So this is what this spatial coordinate system look like. And because this is a function map from R3 to R3, the Jacobian matrix, matrix would be a 3 by 3 matrix. And it will look something like this. T prime. Okay, I'm going to need some room. Where should be this? So these are all with respect to R. Actually, you know what? I'm going to just leave out the close. I might need more room. This is with phi, so therefore it will be Oops. And then with theta, notice that this one is not dependent on theta at all. So therefore you get 0. So that's the Jacobian matrix. And this is probably the last one we're going to do. So hopefully the video will be less than 20 minutes. The last one is cylindrical coordinate system. And this one is actually very nice because remember, this is basically just the polar coordinate system with the R, with the Z added in. So therefore, this is what the coordinate system look like. And so the Jacobian matrix is actually going to be T prime of R theta Z, and that's just equal to this. Oops. So notice that you have these 4 in the top corner that are actually the Jacobian matrix for the polar coordinate system right there. So these 4 things are actually right here. And then you just have this 1 on the bottom corner with a 0 filling the rest of them. Alright, that would be it for 6.5. So in our next video, we're going to start on chapter 7. And that will be integral calculus. Alright, I'll talk to you guys on the next video. Alright, bye-bye.